Hello everyone. Today we are solving the one-dimensional heat equation for a rod of length L. This is a fundamental problem in heat transfer and engineering mathematics. We have a metal rod with both ends kept at zero temperature. Initially, the rod has a temperature distribution given by 5 times sine of pi x over L. We want to find how this temperature evolves over time. The heat equation describes how temperature changes due to thermal diffusion. Our boundary conditions mean the ends are held in ice baths, while the initial condition represents a sinusoidal heating pattern. Let us see how mathematics predicts the temperature behavior. Now let's solve this using separation of variables. We assume the solution can be written as a product of two functions, uppercase x of x times uppercase t of t. Substituting this into our heat equation, we get x times t prime equals k times x double prime times t. Dividing both sides by x times t, we obtain p prime over t equals k times x double prime over x. Here's the key insight. The left side depends only on time, while the right side depends only on position. For this to be equal for all x and t, both must be equal constant. We call this constant negative lambda. It's negative because physically we expect the temperature to decay over time, not grow exponentially. This gives us two ordinary differential equations to solve. Let us solve the special equation first. The general solution to x double prime plus lambda x equals 0 is a cosine of square root lambda x plus b sine of square root lambda x. Now we apply our boundary conditions. At x equals 0, u must be 0 for all time. This means uppercase x of 0 equals 0, which gives us a equals 0. At x equals L, we also need uppercase x of L equals 0. This gives us b sine of square root lambda L equals 0. Since we need a non-trivial solution, b cannot be 0. Therefore, sine of square root lambda L must be 0. This happens when square root lambda L equals n pi, where n is a positive integer. Solving for lambda, we get lambda n equals n squared pi, I'm sorry, we get lambda n equals n squared pi squared over L squared. So our special eigenfunctions are x sub n of x equals b sub n sine of n by x over L, where n equals 1, 2, 3, and so on. N is basically just positive integers. Now for the time-dependent equation, we have t prime plus k lambda t equals 0. This is the first order ordinary linear equations with solution uppercase T of t equals c times e to the negative k lambda t. Substituting our eigenvalues lambda n equals n squared pi squared over L squared, we get t sub n of t equals c sub n times e to the negative k n squared pi squared e over r squared. We will notice the exponential decay. Higher bounds corresponding to larger n values, the faster decay. This makes physical sense, that is, more complex temperature patterns smooth out more quickly due to thermal diffusion. The decay rate is proportional to n squared, meaning the second mode decays 4 times faster than the first, the third mode 9 times faster, the fourth mode 16 times faster, and so on. By the principle of superposition, our general solution is the sum of all modes u of x t equals the sum from n equals 1 to infinity of b sub n sine n pi x over L times e to the negative k n squared I squared t over L squared. To find the coefficients b sub n, we apply our initial conditions. At t equals 0, u of x comma 0 equals f of x equals 5 sine ix over L. This gives us the sum of b sub n times sine n pi x over L equals 5 sine I x over L. Since sine functions with different frequencies are orthogonal, we can immediately see that b sub 1 equals 5 and all other b sub n equals 0. This is a special case where our initial conditions exactly matches one of the eigenfunctions. Therefore, our solution is simply u of x comma t equals 5 sine pi x over L times e to the negative k pi squared t over L squared. With t equals 1 and k equals 1, our solution simplifies to u of x comma t equals 5 sine pi x times e to the negative pi squared t. Let's calculate the temperature at x equals 0.6 and t equals 0.05. Substituting these values, u of 0.6, 0.05 equals 5 sine of 0.6 pi times e to the negative pi squared times 0.05. First, sine of 0.6 pi equals sine of 108 degrees, which is approximately 0.9511. Next, e to the negative 0.05 pi squared equals e to the negative 0.4935, which is approximately 0.6133. Therefore, u of 0.6, 0.05 is equal to 5 times 0.9511 times 0.6133, which gives us approximately 2.92. Let us summarize what we have learned. We solved the heat equation using separation of variables, which transformed our PDE into two ODEs. The boundary conditions gave us eigenvalues and eigenfunctions, while the initial conditions determined the coefficients. The solution shows exponential decay in time while maintaining a sinusoidal spatial profile. This represents how heat diffuses through the rod, with the temperature gradually approaching zero everywhere. This methodology applies to many engineering problems: heat dissipation in electronic components, thermal management in buildings, and material processing, etc. Understanding these mathematical techniques is crucial for designing efficient thermal systems. Thank you for watching.